Here we go. Chapter 5. So the recording, by the way, from yesterday, if anybody asked, I think probably most of y'all were there, but that is posted to Blackboard now, where we covered chapters 1 through 4. And chapter 5, if you remember, was all about chemical reactions. We learned how to balance and classify chemical reactions. And that was setting us up for chapter 6, where we learned to use chemical reactions to calculate like mole to mass ratios and things like that. So balancing, tips for balancing. Again, some of this stuff, just take mental notes as we go. Some of this stuff you'd be like, I got that. I remember how to balance. Balancing's easy for me. You know, don't spend time studying balancing then if you feel good. But if you are unsure about how to classify between a precipitation acid-base reaction, maybe spend time focusing on that. We said some tips when you balance elements by themselves. Save those for last, okay? It could be a diatomic that's by itself. It could just be an element. But you can balance that without messing up anything else. Another thing is if you have a polyatomic, such as hydroxide or carbonate or something, and it's present on both sides, the reactant and the product side, treat it as a single unit. Okay, so for example, carbonate is CO3. If you have this on the reactant and the product side, you don't have to balance the carbons and the oxygens separately. You just say, okay, I have one carbonate on this side or two or whatever. How many do I have on the other side? And get those balanced that way. Classifying chemical reaction. We did a whole lab on this, by the way. So if you want practice, you can just re-download the lab and practice. I mean, there's like 25. It's crazy. There's a lot of stuff to balance on there. So classifying chemical reactions. So we talked about these first 5: synthesis, decomposition, single, double, displacement, and combustion. And we also looked at the more complex types. So that was the precipitation, acid, base, and redox. But here's synthesis. Synthesis is when you have things combining. Okay, such as A and B make AB. Okay, or it could be 3 things, such as A, B plus C make ABC. Okay, it's just things are combining. I don't remember which section we talked about. We associate all these with different relationships. So this is like someone's getting married. Decomposition is divorce. Okay, so it's the opposite. AB is decomposing into A and B. All right, or ABC is decomposing into A, B, and C. So it's the opposite. Synthesis and synthesis is also known as combination. It's the opposite of decomposition. Single displacement. This is when you have something by itself, like an element, and then you have a compound. Okay, so this is when you have, I'm going to zoom in, this is when you have an element and a compound. So it looks like this. We have element A, and then we have compound BC. Now, if element A is a metal, we know metals form cations, right? Metals form cations. So which portion of BC would it displace? Well, it is an ionic compound. The metal will displace the cation, which is going to be B. We always write cations first. That would be the plus and that would be the minus. All right, so metals form cations. So what we would get is AC plus B. A would displace B. Now, if you have A and it's a non-metal, such as chloride, fluoride, bromide, oxygen, and then you have BC, plus minus ionic compound, A will displace C. So you get BA plus C. Excuse me. All right. Double displacement is when you have 2 ionic compounds. Both are compounds. So, for example, you got AB and you got CD. And if we write in the charges, we got cation, anion, cation, anion. So the cations are going to switch and combine with the different anions. So we get AD and C, you got to write C first, B. And that's the only arrangement you can get. Okay, combustion is when you have a carbohydrate, so something that has just carbon, we don't know how many, and hydrogen, we don't know how many. It's a carbohydrate. The only elements in the compound are carbon and hydrogen. And you have oxygen, all right? So when this happens, CH plus O2, you get the same products every single time. You get CO2 and you get water. Okay. So be ready to classify reactions that way. I'm trying to zoom out. There it goes. And then the 3 complex types of chemical reaction, there's a great practice problem in your textbook, 5.34, if you want to look at that. And it's even, so the answers are in the back. We had precipitation. We had acid, base, neutralization, and then we had redox, oxidation reduction reactions. So for precipitation, that is when you have things that are like compounds, such as, it usually looks a whole lot like double displacement, so like AB, but these are aqueous, CD, and it's aqueous. And then on the product side, you get something that's not aqueous. So if they switch and you end up with AD, let's say that forms some sort of solid. S does not stand for soluble here, it stands for a solid. That is your precipitate. And then you get CB, right? And that one is still aqueous. Rarely do you form products where they're both insoluble. Usually just one. We say it falls out of solution. All of a sudden you see the precipitate. And remember, I actually have, so you all get that written down. I'm going to scroll down to the solubility rules because we'll have this on your resources page. Here they are, okay? So you can always write your products and then look at those products and say, okay, do I have any of these cations or anions in my product? If so, then it's probably aqueous. It's probably soluble or aqueous. It's not a precipitate. There are exceptions though, okay? It could have chloride, bromide, or iodine, and if that's paired with any of these cations, silver, mercury, or lead, then it could be a precipitate. Okay, if it's an exception, it is insoluble. But all these up here, a lot of these cations, acetate, perchlorates, nitrates, anions, if that is the cation or the anion that's present in the compound, it will always be aqueous. No exceptions. But if you get something like PbCl2, then that is a precipitate. If you get something like BaSO4, that is a precipitate. And we write S there for the fact that it is now a solid. It's no longer aqueous. Okay, questions on how to use the solubility chart? Okay, remember, if it's in this list, it is soluble, it is aqueous. Unless it's an exception. Okay, so let's go back up. Acid base. These should be super easy for you guys now that we've done chapter 10. You should be able to spot an acid-base reaction, okay? And you're going to have that acid-base chart. So you can always, if you're unsure if it's acid or base, look at your reactants and see if you can notice any of the acids from your table. You can always double check that way. So you have some kind of acid, we abbreviate it HA, and then we have some kind of metal hydroxide, okay? Or you could have something like NH3 could be a base, or water sometimes can act like a base. But then when these things rearrange, especially when you have hydroxide here, you get water. You won't get water if ammonia, NH3, is your base, but you can still have acid-base reactions if a hydrogen is transferred, right? And then we would get some sort of salt, which would be the metal and the anion from the acid. We'll call it a salt. Okay. So now that we've talked about acid-base reactions a lot, I wouldn't expect that one to be too hard to identify for you guys. Redox, we have oxidation and reduction. So what is oxidation and reduction? I'm going to zoom in first. Actually, no, I'm not. Oxidation, remember oil rig? Okay, oxidation is the loss of electrons, okay? Losing electrons. So what happens to the charge? We say charge. What happens to the oxidation number? The oxidation number increases. I'm going to write charge because it's the same idea as charge. Charge increases, okay? Reduction is when you're gaining electrons. So what happens to your charge or your oxidation number? Is reduced. That's the way I like to think about it. If reduction is happening, your charge is being reduced. It's going down. It's becoming more negative. All right, we just went over the solubility rules, so I'm going to go over the rules for how to assign oxidation numbers, and then I think we have a few to practice. All right, here's 4 rules for it. Anytime there's like rules for stuff like this, maybe just have these slides quickly available. That way, you don't have to go digging for them. Like the rules for Lewis structure or the rules for geometry. I like to have those handy on an exam. Okay, an atom in its elemental state, what does that mean? Something by itself. When you have something such as chlorine or oxygen or hydrogen or just something even plain by itself, magnesium, it's by itself. It's in its elemental state. It's not charged. It has an oxidation number of 0. Okay, if it's a monatomic ion, the oxidation number will be equal to its charge. We really don't see those often. Okay, we usually see things in a compound, and there you're going to give it the same oxidation number as its charge as an ion. So if you have something like NaCl, we say the oxidation number of sodium is a +1 oxidation number. Chlorine is a -1. It matches what their monatomic or what their charges for the ions are. All right, lastly, the sum of the oxidation numbers in a neutral compound is 0. See how these add up to 0. Any neutral compound, they add up to 0. All right. So let's do some practice. Which element is oxidized? Which one's reduced? So let's look at this first one. You have silicon and chlorine make silicon tetrachloride. So what oxidation number should we give silicon and chlorine on the reactant side? Rachel says 0, and she's correct. And then what should we give them on the product side? They've got to add up to 0. So we always assign the positive oxidation number to the first element written as though it's a cation. We always assign the negative oxidation number to the second element as though it's an anion. So I know whatever, I'm going to split this in half. This is going to be my positive side, this is going to be my negative side. And they have to add up to 0. So what should we give chlorine? The charge on chlorine, or the oxidation number here, should match its charge as an anion. What charge does chlorine carry as an anion? Brooklyn said -1. That's right. And we got 4 of them. So we got -1, -1, -1, -1. That's a total of -4. So the positive side has to be +4 to make it add up to 0. And I just have 1 silicon. So that is the oxidation number for silicon. So then what I do is I come over here. I say, okay, how are these things changing? How is the charge or the oxidation number changing? Silicon's going from 0 to a +4. Chlorine is going from 0 to a -1. You're not writing the totals. It just so happens that the total here matches what the oxidation number is for silicon, but I'm not writing that chlorine is going to a -4. You look at the individual chlorine and write what that oxidation number is going to. So silicon is increasing in its oxidation number, so it must be giving away electrons, so that is oxidation, it's oxidized. Chlorine is being reduced, so it must be receiving electrons, so that is reduction.
So because they were by themselves at the beginning, that's why they're 0?
That's right, Madison.
Okay.
So I bet you can tell me what chlorine is going to be on the next one.
0.
Yeah. Anything else going to be 0 in this one?
The BR on like the product
Yeah.
side.
Yep. Okay, so now what about sodium and bromine right here in this compound? What do y'all think?
Is the sodium +1?
Yes, Zoe.
Okay.
And then the bromine has to be -1.
Mhm.
And then over here, we actually did NaCl right up here, +1, -1. Okay. So chlorine, sodium, bromine, what's happening to these? Chlorine starts out as a 0, and on the product side, you always write what it was on the reactant side and what it becomes on the product side. So it becomes a -1. Sodium starts as a +1, and on the product side, it's still a +1. So I'm not even concerned with sodium here. It's not changing. It's not being oxidized or reduced. Bromine starts out as a -1, and on the product side, it becomes a 0. So what do y'all think? Yeah, Grayson, both compounds were a +1, -1. Maddie said, so the coefficient, nope, coefficients have nothing to do with it. That's just for balancing. Yeah, you are not paying attention to these numbers when you're assigning oxidation numbers. Okay, so chlorine is going from 0 to negative, so it's being reduced. So that is reduction. And bromine is going from -1 to 0, so its oxidation number is increasing, so that is oxidation, being oxidized. You will always have both happening together, oxidation and reduction. If something's being reduced, something else has to become oxidized. They work in tandem. All right, this last one, let's go ahead and go through and assign the easy parts. Anything by itself is a 0. So I'm going to write underneath, chlorine here has to be a 0. All right, Sb is antimony. We don't see that element a whole lot. SbCl3. So remember, it has to add up to 0 in a compound. The oxidation numbers have to all total add up to 0. So chlorine, anytime chlorine's in a compound, its oxidation number matches what it would be as an anion, and it will always be a -1. We got 3 of them though, so the total amount of negative charge here is a -1, -1, -1. So we got 3, so it's a -3 total. I just have 1 antimony, so whatever the total amount of charge has to be, which we know it has to be a +3 to make everything neutral and add up to 0 for the compound overall. And I just have 1 antimony, so its oxidation number is +3. We don't divide by anything here because we just have 1 cation of sorts. Over here on the product side, now we have 5 chlorines. We know chlorine is always a -1. But we got 5 of them, so the total amount of negative charge here is a -5, since we've got 5 things that are all -1 each. And then so the Sb, we just have 1, so it's got to match. It's got to be a +5 to make these things add up to 0. All right, so what's happening overall? Sb and then Cl. Antimony is going from a +3. On the product side, it is a +5. Chlorine, what do y'all think about chlorine?
Is it just -1 to -1?
Well, you do have some chlorines that are -1. These in the compound, those 3 chlorides, they're -1 and they stay -1 over here. But what about these chlorine atoms? So you have some that are, yeah, they're -1 on both sides. Those 3, there's 3 of them that aren't changing, but there are 2 chlorine atoms. Now again, we're not counting in coefficients here, but I'm trying to make the point that I do have some chlorine atoms that are changing. They're going from 0 to -1. Some are already a -1, they're not changing, but I do have some chlorine atoms that are going from a 0, and then they're all -1 on the product side. So this one's being reduced, and antimony is being oxidized. Does that make sense? So that's redox. You're trying to track what is changing charges.
Can it sometimes be that imagine the first Cl, now it's like the first one is -1 and the last one is also like -1 and the one is at 0. But can it sometimes be that we have two like Cls that change? I don't know, does it make sense or not?
Say your question again, Zoe.
Okay, the first compound, the Cl is -1, right?
Right.
And then we go to after the reaction, let's say it's also -1.
Right.
So I know we cannot, like, that's the same. But is it possible, imagine, that we have 2 Cls, now we have only like the plus Cl2, that we have 2 of them, they change? Or that's not an option?
We do have 2 of them that are changing. 3 of our chlorines, let me erase. These 3 chlorine atoms are not changing, but these 2 chlorine atoms are changing. And those are the ones we're saying are being reduced.
Yeah, okay, wait. Can it be that 2 Cls change, but like a different change?
Oh, no, chlorine always goes from like -1 to 0 or 0 to -1.
Oh, okay.
Yeah.
Okay.
Chlorine
Okay.
and fluorine and bromine, they'll be pretty predictable like that.
Okay, thank you.
Yeah. Not every atom is predictable, but there are certain ones that they invariably, like oxygen. Oxygen's either going to be a 0 or a -2. So it can go from a -2 to 0, or it could go from a 0 to a -2. But certain atoms are not, we can't always predict what they'll be. All right, so that's chapter 5, balancing and classifying. All right, chapter 6, mole mass relationships. This is where we introduced Avogadro's number. So we started talking about this idea of a mole. It's useful because we work in terms of mass, not in terms of molecules, but our body thinks in terms of molecules, and it deals with molecules all the time. So we say 1 mole of any substance is the amount of the substance in grams that's numerically equal to its formula weight in AMUs. A formula weight in AMUs is just how much one individual molecule weighs in atomic mass units. But when we scratch out AMUs, so like, for example, CH4 would be how many AMUs? 12.011 plus 4, so it'd be around 16.05. Well, AMUs, that's how much one individual molecule of CH4 weighs. But the moment we say, let's just change this to grams, now we have 1 mole. That's how much 1 mole of CH4 weighs, that many grams. Okay, so we didn't change the number, we just changed the unit, and now we have a mole of that substance. Okay, and then we also said, okay, I don't know if I can move this over. No, I can't. Avogadro's number is the number of items in 1 mole. So if we want to know how many molecules of CH4 are present in 16.05 grams, if it's 1 mole of the substance, then we have Avogadro's number of that molecule. And Avogadro's number was 6.022 times 10 to the 23rd. This is how many items are in 1 mole, okay? In chemistry, in the world of chemistry, we're usually just discerning or determining the number of atoms or molecule in a mole, atoms or molecules. So again, if I said you have 16.05 grams of CH4, how many atoms or how many molecules are present? Because this is 1 mole, you know that it's this many molecules, Avogadro's number, okay? If I had half a mole, you would just divide this number by 2. If I had 2 moles of CH4, you would multiply this by 2. And then we use this relationship to calculate molar mass. So we can determine this information for any compound. So let's say we have a compound known as urea, which is CO, and we have NH2 with a parentheses of 2 around it. If I want to calculate the molar mass, how much does 1 mole of this substance weigh? We go to the periodic table, which I have right here. And we say, okay, in 1 molecule, I have 1 carbon. Well, I'm just going to write it out like this. I have carbon, I have oxygen, I have nitrogen, and I have hydrogen. So carbon on the periodic table weighs 12.011. 1 mole of carbon would be that many grams. And then 1 mole of oxygen atoms is 16.0 grams. 1 mole of, well, how many nitrogens do we have in our molecule here? We've got this 2 on the outside of the parentheses, so we have 2 of those, and we got 4 hydrogens total. You multiply everything inside the parentheses by the subscript outside the parentheses. So I've got to do 2 times, for nitrogen, it's 14.01. And 2 moles of nitrogen is going to be 2 times 14.01. And then for hydrogen, I've got 4 of those, so 4 times 1.01. And then you just add all this up. 28.02 and 4.04. So what we should get total, I'll write it over here on the side, would be, well, 28 and 28 is 56, and that should be 60.071. Is that what y'all get? I think that's what I get. So that's how many grams of urea are in 1 mole. And then I said, how many molecules is this? How many molecules of urea are present in 60.071 grams? You would tell me Avogadro's number. If you have 1 mole of a substance, you have Avogadro's number of that item. Okay, then we talked about how we can use molar mass to convert between grams and moles. Molar mass. We use Avogadro's number to convert between moles and molecules, or moles and atoms. But we use molar mass to convert between grams and moles. So here is an example of that. The active ingredient in milk of magnesia is an antacid. It is magnesium hydroxide, okay? And it tells you the formula, MgOH2. A typical dose, which is 1 tablespoon, contains 1.2 grams of MgOH2. Calculate A. So we got a 2-part problem here. Part A says, calculate the molar mass of magnesium hydroxide, MgOH2. So we're going to do exactly what we did for urea. Magnesium, we just got 1 of these, 24.305. We got oxygen, we got 2 times 16. And hydrogen, we got 2 times 1.01. So it's 32 and 2. Just add all of this up. Oh, guys, why am I even doing this? How many of y'all would do something like that on the exam? You just like start working the first part of the problem and you're like, oh, the answer is given to me at the end. Okay, ignore that part. We already did part A. It's 58.32. Part B says the amount of magnesium hydroxide in 1 in moles in 1 tablespoon. So how many moles of magnesium hydroxide are in 1 teaspoon, not tablespoon? So we say 1 tablespoon, let's write out our relationships. 1 tablespoon, TBSP, is 1.2 grams. How many teaspoons are in a tablespoon? Anybody know?
3.
Yep. 3 TSP, teaspoon, in 1 tablespoon, TBSP. And then we know there's 58.32 grams of magnesium hydroxide in 1 mole. So I want to know how many moles are in a teaspoon. How many moles are in a teaspoon? Well, I know for every 1 mole, there are 58.32 grams. And the reason I'm starting here is because I want units of moles on my answer, and I want it on the top. So I'm just going to go ahead and put that unit on top where I want it. And then I'm going to cancel everything else. I know there's 1.2 grams per tablespoon. And then I know there's 1 tablespoon for 3 teaspoons. So you see that grams will cancel, and then tablespoons will cancel, and then you'll have per teaspoon. So moles per teaspoon essentially be your unit. So you do 1 divided by, yeah, let me know what you get. Calculate it with me. You can't ignore the 58 on the bottom. 1 divided by 58.32 times 1.2 divided by 3. So I got 0.00, we'll just say 69 moles of MgOH2 per teaspoon. Okay, Brooklyn got that as well. So you see how we can use molar mass to convert, we were given the number of grams, and then we calculated how many moles in a certain amount. Okay, questions there? Would y'all feel confident with something like this on the exam? I've seen different. Okay, it's three steps there, so hopefully not too bad. We've done worse. Another one. We have to practice a problem where we use mole ratios. So this is what I call the 3-part problem. We had 3-part problems in chapter 6, and we did them again in chapter 9, but with molarity. So mole ratios, here's 6.56. Zinc metal reacts with hydrochloric acid according to the following equation. So you got zinc, it's a solid metal. You drop it in some acid, you're gonna get a double, or no, sorry, what kind of, you guys tell me. It's not a double displacement. What kind of reaction is this? Synthesis, decomposition, single, or combustion, since I already eliminated double. Molly says single displacement. She is correct. The zinc, I'm on eraser. The zinc is displacing the hydrogen. You see that? So single displacement there. Okay, how many grams of hydrogen are produced if 15 grams of zinc react? So you see what's happening? I'm giving you information on this substance, and I want to know something on that substance. Anytime you're given information on one reactant or product and you're asked for information on the other one, you've got to use a mole to mole ratio. And if we're going to use mole to mole ratio, then we've got to convert this amount of grams to moles. And this is where molar mass comes in. So here's the order. We're going to start step 1. You're going to convert grams of zinc to moles of MOLS, moles of zinc. Step 2 is you're going to convert moles of zinc to moles of, why do I keep writing MOS? Moles of hydrogen. And then step 3 is you're going to convert moles of hydrogen to grams of hydrogen. Those are the 3 steps. molar mass, then a mole to mole ratio, then another molar mass. So 15 grams of zinc. What is the molar mass of zinc? You just look at the periodic table. Nothing to calculate here. It is 65. There's 65.38 grams for every 1 mole of zinc. And please write in the element or the compound or whatever. Because now when I plug in step 2, the mole to mole ratio, I already see that I have moles of zinc on the top in my previous step. So that lets me know I've got to put moles of zinc on the bottom. And what's my mole to mole ratio? It looks like it's 1 to 1. For every 1 mole of zinc, I'm going to get 1 mole of hydrogen. Now, my last step was to convert moles of hydrogen to grams, and you always do that with a molar mass. So for H2, remember here it's a diatomic. People will forget this and they'll just plug in 1.01. But for every 1 mole of H2, I have 2 hydrogen atoms, so it's 2.02. All I did there was say, okay, hydrogen, I've got 2 times 1.01. That's the number off the periodic table. It's grams here. So for every 1 mole of H2, it is 2.02 grams. And that is what I'm plugging in right there. And I see so far grams of zinc cancel, moles of zinc cancel, moles of hydrogen cancel. And now I'm left with grams of H2, which that's how many grams. That's what the question's asking for. $15 divided by 65.38 times 1 divided by 1 times 2.02. What do y'all get? Whoops, not that. .46 grams is what I got. Questions there? All right. Another example here. Kidney stones. Anybody ever dealt with kidney stones before? I hear they're awful. Somebody has once compared them to having a baby. And if that is true, I know what that's like. But if that is true, then God bless. I hope I never, ever, ever get one. My father-in-law has literally had hundreds of them. It's nuts. They have to go in and bust them up with lasers all the time. All right, principal component of kidney stones is calcium oxalate, CaC2O4. A kidney stone recovered from a typical patient contains, look at that, 8.5 times 10 to the 20 formula units. That's like formula units here is just that many molecules of calcium oxalate. How many moles of calcium oxalate are present in this kidney stone? What's the mass of the kidney stone in grams? So what we're given is we're told that there are 8.5 times 10 to the 20 molecules of CaC2O4, calcium oxalate. And we want to know, the first question is how many moles of calcium oxalate are present? How do we convert between molecules and moles? Somebody knows. Yes, Avogadro's number. Okay, Avogadro's number says there are 6.022 times 10 to the 23rd molecules in 1 mole. Now, please, when you divide by this in your calculator, put that number in parentheses. I guess I could grab my real calculator. Okay, I got 0.0014. That's what Brooklyn got, moles. Okay, the last question says, what is the mass in grams? So now we just take this 0.0014 moles, Ca, C2O4, and we convert it to grams. How do we do that? I want to cancel moles, so I know that unit has to go on bottom. And I want grams on top. Molar mass, thank you, Maddie. Which is what? Calcium is 40. Plus we got 2 carbons, so that's 24.022 plus 4 oxygen. So 16 times 4 is 64. So total, I got that there's 128.1 grams for every 1 mole. All I did was calcium is 40.078. I've got 1 calcium. I have a 2 carbon, so I did plus 24.022. That's the 12.011 times 2. That was the carbon. And then plus 64 for my oxygens, 4 oxygens, 16 times 4. So now we do 0.0014 times 128. And we get that there is 0.179 grams of calcium. So we know a dollar bill weighs about a gram. So fortunately, this kidney stone, actually, I don't know if that's big or small. I don't know what the average kidney stone is. I've heard people can have kidney stones the size of golf balls, but I don't know how much that would weigh. So I don't know if that's big or small. It doesn't seem big to us, but I'm sure to our kidneys, it might seem big. All right, chapter 7. So that's chapter 6. Some good practice with converting between moles and mass. This is the next big chapter. A lot in chapter 7. There are like 6 big topics, all within chapter 7. The first one was enthalpy. So we talked about the law of conservation of energy. We said that all chemical reactions have energy associated with them. We got to invest energy and we've got to we release energy. So we said breaking bonds requires an investment of energy, and forming bonds releases energy. This is why ATP is important in our bodies, okay? We always have chemical reactions in our bodies that require energy, and they're not favorable. So our body has to have some kind of resource that can provide energy to power those reactions. And that's where ATP comes in. When ATP is hydrolyzed, okay, when it's broken apart, it releases a lot of energy, and that energy is harnessed to power other chemical reactions, okay? That's just an example, but enthalpy, entropy gives free energy. We learned how to calculate delta H, and then we learned how to calculate or judge the sign of delta S, and then we learned how to put it all together and calculate delta G. So delta H, we said delta H is equal to the sum of the enthalpy of the reactants minus the sum of the enthalpy of the products. So you look at what bonds you have, and did I put that bond table energy on here? No, I didn't. Did I? No, I didn't. That will be on your resources page, the table of bond dissociation energies. And you do consider your coefficients. So earlier, Maddie was asking about coefficients when we were doing redox. So those don't matter then, but coefficients do matter here because that will tell you how many bonds total you have. And you always multiply the number of bonds within the molecule by the coefficient of the molecule. And then you add it up on all the reactant side minus the total on the product side, get your delta H. Usually the units are kcal per mole. It could be kilojoules per mole, kJ per mole. Endothermic, exothermic. You guys remember which one's which? Endothermic, is that a positive or a negative delta H? If you get what is endothermic? If I have an endothermic reaction, that means I have a positive delta H overall. Exothermic is negative delta H overall. So if I'm doing a reaction in a test tube and I'm holding it, for an endothermic reaction, I will feel the test tube get cold because the substance within the test tube is absorbing heat. And I feel the absence of heat from the surroundings, okay? The exothermic reaction, the test tube would get warm, it would get hot. And I feel the release of heat from the substance in my test tube. All right, which one's favorable? Which one's favorable overall? Exothermic or endothermic reactions? Which one gives you products that are more stable? That's the one that's favorable. Yes, 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 yes. Exo is favorable. Okay. Delta S. When determining the sign for delta S, you have to consider number of moles of stuff on each side. So how many moles of stuff do I have? Like 5 moles of my various reactants on one side, and then I only have 1 mole of products, or whatever. How many moles of stuff do I have on each side? And then 2, you have to consider the physical state. Physical state, okay? Remember that a positive delta S, so entropy disorder, remember entropy is a measure of disorder. That's delta S. A positive delta S could be examples. Let me zoom in on this. Disorder increasing is when you're going from a solid towards a liquid, towards a gas. Okay, if you're have things that are solid or liquid and you're making things that are gases, disorder is increasing. Or if you have few moles, I keep like writing ahead of myself, few moles to more moles of stuff. Negative delta S would be like gas, and then you're making things that are liquid or solid. And then you have a lot of moles. And on your product side, you have fewer moles. Okay, it'd be like a synthesis reaction. Positive delta S would be like a decomposition reaction. Don't just box it into that, but that is an example. Okay, calculating delta G from delta H and delta S. 2 things to check before you just plug stuff in. Number 1, your temperature has to be in Kelvin. And then number 2, units for delta S, convert them to kcal per mole Kelvin. Okay. Usually you're given units for delta S in calories or joules. You need to convert them to kcals or kilojoules, depending on what your unit for your delta H is. All right, now when we do that, remember the equation is delta G equals delta H minus T delta S. A negative delta H and a positive delta S will always give you a negative delta G. Is this endergonic or exergonic? Similar to endo and exothermic, a negative delta G. Maddie said exergonic. Yeah, a negative delta G is exergonic. Positive delta G is endergonic. Okay, now if I have a positive delta H and a negative delta S, I'm always going to get a positive delta G. If I have both positive or both negative, I have to use the equation and calculate what my delta G will be. All right. So I think we have a practice problem here. Following reaction is used in the industrial synthesis of PVC. You guys know what PVC is, like plastic pipe. It's a really hard plastic. I'm sure it's used for more than just pipe. Here's the reaction. Cl2, then you got that molecule, and then you make this big molecule, and you're told your delta H is negative 52 kcal per mole, or it gives you the value in kilojoules. Is delta S positive or negative? Let me erase my scribble. Is delta S positive or negative? What do y'all think? Nobody wants to guess. You got a 50 shot, 50-50 shot. Yep, it's negative. Okay, you have everything that are gases on the reactant side. Product side, you just have liquids. Gases are inherently more disordered. The molecules have a lot more freedom and a lot more energy. Liquids are more ordered. So we're decreasing, disorder is decreasing. So delta S is negative. Is the process spontaneous at all temperatures? So here's what we have. We have a negative delta H and we have a negative delta S. Remember, when they're both negative, what does the equal mean? Oh, right here, this equal, that's a carbon-carbon double bond. Yeah, there's a weird way of writing it. This molecule looks like this. Well, it's a terrible drawing. That's what it looks like. Good question, though. We don't see stuff like that much. Is it spontaneous at all temperatures? What do you guys think? Yeah, the correct answer is no. But now it says explain. So why? Remember, delta G equals delta H minus T delta S. So let's just plug in some random numbers. Let's say we got a negative 10 here, and we have a minus. Let's say temperature is 2, and delta S is a negative 5. Actually, let's make it a negative. Let's make it a smaller number. I'm just plugging in random numbers here. Higher temp can change delta G. It's exactly what I was about to see. So if you add all this up, 2 times 2 is 4. And this all becomes positive when you do the negative and the negative. That becomes a positive 4. And negative 10 and positive 4 make negative 6. So it might be spontaneous at low temperatures. But let's crank temperature up. Let's say now we're not changing delta H and delta S. Let's say now we have a high temperature like 20. It was 2, and now our temperature is 20. And our delta S is still negative 2. So now we have a positive 40 and a negative 10, and that gives us positive 30. So at higher temperatures, delta G could become positive. It could become non-spontaneous. Non-spontaneous. And the opposite happens when you have a positive delta H and a positive delta S. Then at lower temperatures, you're more likely to get a positive delta G. Questions on that? You can only say things like it's always spontaneous or it's always non-spontaneous when you have these conditions, okay? Like when you have a positive and negative or a negative and positive, delta H and delta S. But you have a table for that. Remember, we have a table that has like 4 rows on it. It tells you what you can expect from the different scenarios of the signs on delta H and delta S. Okay, Reaction rates, okay? So what determines how fast or slow a chemical reaction will occur? So we talked about rates. We said certain reactions can go fast, certain can go slow, but it all depends on the activation energy, which we abbreviate EACT. We said if you have, let's draw an energy diagram. This is your delta G, your change in energy. This is the reaction progress. So if you have some energy level for your reactants here, and you have a really high energy barrier before you go and make products, okay, here is my activation energy. I start with the level of my reactants and I climb up to the peak. This is my activation energy. That reaction would be slower than a reaction, say, where my activation energy is like this. And I have now a very small activation energy compared to my first one. So this one would be fast, and this red one would be slow. So if I start them at the same time, the blue would finish first. The other reaction would still be running. By the way, what's my delta G here? Is it positive or negative? You always draw the difference between the reactant level and the product level. And here it's going down, so delta G is negative. You draw an energy diagram like this, where you have reactants, products. Here my delta G is positive. I'm going up. That's reactants, sorry, reactants, products. And you could still also label the activation energy. All right. We talked about efficient collisions, molecules colliding the right way with sufficient energy, all determines the reaction rate. But then we said there's ways you can manipulate it. You can force reactions to go faster or slower. If you increase the concentration of the reactants, if you increase the temperature, or if you add a catalyst, these three things will increase the rate. If you do the opposite of these things, if you decrease the concentration, decrease the temperature, or if you don't add a catalyst, nothing's going to change. But if you decrease concentration or temperature, your reaction rate would slow down. But if you increase concentration of your reactants, or you increase the temperature, you heat those particles up, they'll move faster, they'll collide more often, that would increase the rate. All right, then we talked about equilibrium. So the last two things we have in chapter 7 are equilibrium and Le Chatelet's principle. So remember, equilibrium is where delta G is almost zero, approximately zero. And there you have the forward and the reverse rate, or forward and reverse reactions happening at the same rate. So let's say we have some reaction where AB plus CD, and you get this double arrow, make A, D, and CB. You got a forward and a reverse reaction happening at the same rate. That doesn't mean you have equal amounts of your reactants A, B, and CD, and that they're equal to the concentrations of AD and CB. That just means that your rates are the same. Okay, we can write K for these kinds of reactions and anything, a process at equilibrium. So K would be, it's always the concentration of the products over the concentration of the reactants. And you raise them to the power of their coefficients. So if we had coefficients of, let me just zoom in, 2, 1, I'm just throwing numbers in here. This is not even going to be balanced. Okay. 1, well, actually it would have to be, no, there's no way it can be balanced. 2, 3, let's just say these are our coefficients. Just making numbers up. It's not even balanced. But you would raise it, it would look like this. AD to the power of 2 CB to the power of 3, AB to the power of 2 times CD, and it's just raised to the first power, so we don't have to write anything there, okay? Coefficients do matter here. Now remember, if K is bigger than 1, what does that mean? Are your reactants or your products favored? Do y'all remember? K is bigger than 1. Must mean that your numerator is bigger than your denominator. That's right, Molly. We don't put any solids or anything that's directly liquid. Only things that are aqueous or gas. Only aqueous or gas go in this equation. Okay, so if K is much, much bigger than 1, products favored. Okay, the forward reaction is the dominant one. If vice versa, K is much, much smaller than 1, reactants are favored. It's the at equilibrium, you've got more reactants, and the reverse reaction's dominant. So, okay, we'll just do this one problem really quick, and then we're going to hit Le Chatelier's principle, and then we got to do chapters 8 and 9. We've already been going for like an hour, so we got to finish this up. For the reaction, N2O4 makes 2NO2. Everything's a gas here, so that's good. Equilibrium concentrations at 25 degrees Celsius are, here's the concentration for NO2, 0.032 mole per liter. And for N2O4, it's 0.147 mole per liter. What's the value of K? So we say K is going to be equal to my product squared over my reactant. Coefficient is just 1. So now we say K equals, you just plug your numbers in. NO2 is 0.0325. I'm going to square that, divided by 0.147. And we do have units of molarity here. I should write those in. K is unitless. Whoops. So 0.0325 squared divided by 0.147, you should get 0.00719. So reactants or products, well, K is less than 1, so it's reactants. Now that you have K, what if I said you do another reaction, but you only know that your concentration of NO2 is like 0.15. What's the concentration of N2O4? All you do is you plug in K and you plug in your concentration of NO2, square it, you solve for N2O4, okay? All right. Le Chatelier's principle says when stress is applied to a system at equilibrium, we change something, a concentration, pressure, temperature, that the equilibrium will shift, the concentrations will shift to relieve the stress that we added. All right, so we talked about changes in concentration, temperature, and then pressure and volume. So, I'm just going to write a few things out real quick down here. If we increase the concentration of I'm going to use R for reactant, P for product. If we increase the concentration of reactant, equilibrium will shift. Which way? It'll shift towards the product, so it'll shift towards the right. If you decrease the concentration of a reactant, equilibrium will shift towards the thing you're decreasing, so shift left. If we increase the concentration of a product, equilibrium will shift the other way. It'll shift to the left. If we decrease the concentration of a product, equilibrium will shift towards the thing we're taking away or decreasing. So shift right. Because the products are always on the right side, the reactants are always on the left side. Okay, temperature depends if it's an exothermic or endothermic reaction. So if we have exothermic, that means heat, or your energy term, is a product. Okay, exo, by the way, is negative delta H, remember. If we have a positive delta H, that's endothermic, and heat, whoops. What am I writing here? Heat, I'm trying to write heat, is a reactant. Okay, so first you decide, is it exothermic or is it endothermic? Then if heat's a reactant or if heat's a product, you literally just play it out the same way you do up here. If you increase temperature, if heat's a reactant, which way will it shift? If you decrease temperature, if heat's a reactant, which way does it shift? Vice versa with the products, okay? You just decide if heat is a reactant or a product, and then you play it out the same way you do with concentrations. Okay, pressure. You have to consider the number of moles of gas on each side. Okay, so if you have, for example, let's write it out two ways. Let's say I have 3 moles of gas on my reactant side. On the product side, I have 1 mole of gas. Okay, if you have something like this, if you increase pressure, equilibrium shifts. If you increase pressure, it'll shift to the side with fewer moles of gas. So it'll shift to the, what is that? It's my right. It'll shift right. If you decrease pressure on something like this, equilibrium will shift left. Okay, but what if I have something like 2 moles of gas versus 4 moles of gas? You see how this one's different? Not just that the numbers are different, but now I have more moles of gas on my product side. On the first one, I have more moles of gas on my reactant side. So now, if I'm literally gonna copy, I'm gonna change some things though. So now if I increase pressure, equilibrium shifts left. I decrease pressure, equilibrium shifts right. But it all depends. You got to figure out how many moles of gas do I have on each side. If you increase pressure, it shifts to the side with fewer moles of gas. If you decrease pressure, it always shifts to the side with more moles of gas. All right, that's chapter 7. We got to hit chapters 8 and chapter 9 in like 20 minutes. Can we do it? I'm seeing some very blank stares. Do we need a break? We need a breather? I just want to push through. We're almost done. Yeah, let's get it done. All right, everybody done writing here? That was a lot of writing. All right. Chapter 8 was gases, liquids, and solids. We look at intermolecular forces. So we first talked about understanding 2 things: how intermolecular forces the level of intermolecular forces between solids, liquids, and gases, okay? And then the amount of kinetic energy associated with solids, liquids, and gases. So we said for gas, liquid, solid, zoom in, these have high kinetic energy, lots of kinetic energy. Solids have low kinetic energy. And liquids are always in the middle. But gases have very few intermolecular forces, IMF. And the solids have a lot of intermolecular forces. Intermolecular forces is IMF. Okay, so we talked about those things, and then we said how arrangement or energy changes when matter undergoes a transition between the phase. So melting, condensation, sublimation. If you are something that's a solid and you're melting, becoming a liquid, you have to absorb heat. Okay, that's endothermic. If you are if you're evaporating or boiling, you have to absorb heat. That's endothermic. Anytime you're going down from a gas towards a liquid or towards a solid, you're releasing heat. That's exothermic. Okay. We had a whole chart for that. We wrote those in on chapter 8 slides. All right. Next slide. Oh, we'll look at a practice problem. So we talked about London dispersion. This was the weakest. These occur in all molecules. They are in all molecules, but they are dominant, or they're the strongest in non-polar molecules. Okay. As surface area increases, the amount of London dispersion forces increase. And as atoms get bigger and have more electrons, we said these are created by, remember, momentary or temporary, I'll just write temporary dipoles. That's what creates van der Waals or London dispersion forces. Sorry, I gotta turn my space heater on. Okay, dipole. That's another kind. This is stronger than London dispersion, but weaker than hydrogen bonding. And these are created in polar molecules. Polar molecules have dipole forces. So it's a permanent dipole, okay? One that does not cancel. So if there's symmetry in your molecule, you have a nonpolar molecule, that's not going to have a permanent dipole. It won't experience dipole forces between molecules. We said when you have molecules that have dipoles, they align themselves. I'm going to draw a little picture. I'll zoom back out. If you have two molecules like this, and you have like a semi-positive region and a semi-negative region, okay, they're going to line themselves up where the opposite partial positive and partial negative of different molecules are aligned. And then you'll get the dipoles between the molecules. All right, that's dipole. We're gonna practice this in a second. Hydrogen bonding, this is the strongest. And we said you have to have two things. One, you have to have a semi-positive hydrogen, a positively polarized hydrogen. Two, you have to have a lone pair on an oxygen, nitrogen, or fluorine. Okay. And then the biggest thing, how this applies, I wanted you to understand how this affects boiling points and melting points. So if I give you three molecules and one's a nonpolar molecule, one's polar but can't hydrogen bond, and one can hydrogen bond, how are you going to order these? Well, hydrogen bonding is the strongest type of intermolecular force holding molecules together. That takes the most amount of energy to break molecules apart if they're hydrogen bonded together. So they would have the highest melting point or boiling point. If something's held together by London dispersion forces, those molecules are going to have the lowest melting points or boiling points. It takes the least amount of energy to melt or boil molecules like that. So we're only going to do like 3 of these. Identify the predominant intermolecular force. Let's just do B, let's just do E, and let's just do F. So draw the Lewis structure, HCN. What do y'all think? You'll have an electronegativity chart on your resources page. Hydrogen carbon bonds are nonpolar, but the carbon nitrogen bond, this is polar. Polar bonds right there, that triple bond. So we draw a dipole in, pointing towards the more electronegative side. So we got the partial positive on the carbon, and we got a partial negative on the nitrogen. So this is a polar molecule. So the dominant force there would be dipole-dipole. Okay. CH3Cl. Okay. Carbon hydrogen bonds, again, none of those carbon hydrogen bonds are polar, but this carbon chlorine bond has a difference in electronegativity difference of 0.5. So that bond right there is polar. So again, we can draw a dipole in where the carbon is the partial positive, chloride is the partial negative. So dipole, dipole here. What about F? We've got CH3, COOH. What do y'all think? Brooklyn said hydrogen bond, that's right. So this hydrogen right here is positively polarized. So this, is it a donor or an acceptor? Yeah, remember we labeled the parts of the molecule that can hydrogen bond, donor and acceptor. Is this the donor? Is the hydrogen? It's the donor. And the lone pairs, all these lone pairs, these are acceptors. So this, the strongest force at play here is hydrogen bonding. If a molecule has a donor and an acceptor, it can hydrogen bond with an identical molecule like itself. If it only has a donor or an acceptor, it can still hydrogen bond, but maybe not with itself, just with like a water molecule or a molecule of ammonia or something. All right, questions there? I think we're almost done. I think we got gas laws and then chapter 9. Hang in there. All right, gas laws. Yeah, how many slides we got? 1, 2, 3, 4. Why did I keep going? 5. Okay, we have 5 slides left. Okay. We talked about gas laws. We talked about units of pressure. 1 atm equals 760 millimeters of mercury equals 14.7 psi equals 101.325 pascals. I bet y'all like, do you just sit around and memorize these numbers in your spare time? Yeah, that's what I do. No, I don't. Combined gas law. So we had Boyle's law, Charles' law, Gay-Lussac's law, but they all combine into the combined gas law, which is P1 V1 over T1 equals P2 T2 over. Whoops, that's not right. V2 over T2. This is an example problem here. A compressed air tank carried by scuba divers has a volume of 6.8 liters. I'm just going to call this V1. It's the first volume I'm given. How do I know it's volume? Units of liters. A pressure of 120 atm, so I want to call that P1. What is the volume? So I'm looking for V2. If we have 0 degrees Celsius. Oh, by the way, this is my first temperature, T1. What's the volume of the air tank at 0 degrees Celsius? So that is T2 now, and a new pressure, 1 atm, that's P2. So just plug everything in and solve for V2. So first I'm going to rearrange the equation. If I'm going to rearrange this, I'm going to multiply by T2 on both sides, and I'm going to cross divide by P2 to move that over. So when I do that, I got P2 on top, P2 on bottom, it cancels, and then the second temperature also cancels on the right side. So now I have V2 is going to equal all of this. T2 times P1 times V1 divided by P2 times T1. Now you just plug it in, and you got to make sure units for pressure, ATM and ATM, that's good. But we got to convert the Celsius here. It's got to be in Kelvin. So let's convert our temperatures to Kelvin. So we got the first temperature is 20 degrees Celsius plus 273.15. That equals 293.15. And 0 degrees Celsius is, is just 273.15. So that's my T1, and this is my new T2 in Kelvin. So now V2 is going to equal 273.15 Kelvin times 120 ATM times 6.8 liters. Divide all of that by 1 ATM times 293.15 Kelvin. And I got the volume of air in the tank would be 760.3, is that right? Liters? That seems really big. 2 I think that's right. Divided by 293. Just seems really big, but that's what I got. Do I get something different? Okay, ideal gas law. Remember, ideal gas law is PV equals nRT, and your R is a gas law constant whose value is 0.0821. And you got lots of units here. We got units of liters times ATM over, should be moles times Kelvin. Here's an example problem. You'll be given 4 of the 5 pieces, and you're solving for something. So it says if 15 grams of CO2 has a volume of 0.3 liters, so there is our volume. 310 Kelvin, there's our temperature. We already know R, what's the pressure? So we're solving for pressure. It says in millimeters mercury, by the way. So I don't have moles, I don't have N. Pressure, if I rearrange my equation, PV equals nRT equals nRT divided by V, right? So I need to plug in moles, but I need moles. I don't have moles of CO2, I have grams of CO2. So all I gotta do is take that 15 grams of CO2 and say, okay, what's the molar mass of CO2? We'd have to calculate that. It should be 12.011 plus 32. So That would be 44.011 grams per 1 mole. And I would get 0.341 moles CO2. Now this I can plug in for N. This is N. So P equals, I got liters. You got to make sure all your units match the units for R. So I got 0.341 moles. I'm going to zoom in, times R, which is 0.0821. Units there are liters, ATM, mole, Kelvin, and then times T, which is, I'm going to just scoot all this over. Like is not reading my fingerprint. Never mind. I'm going to squeeze it in, 310 Kelvin. And you divide this by volume, which is 0.3 liters. So what we'll get is I got 28.9, and this will be ATM, but the problem says, what is the pressure in millimeters mercury? So my last step here is I'm going to convert. I know that there's, for every 1 ATM, it's 760 millimeters of mercury. What a problem. I'm going to write my answer down here. 2197, we'll just say 5, I'm rounding. So we use the ideal gas law, but we had a couple extra steps. We had to convert grams to moles, and then we had to convert pressure to millimeters mercury in the end. But that's an example with the combined gas law and ideal gas law. Okay, last chapter. We can do it. Hang with me. We've been going for an hour and a half. Everybody got everything written down from this problem? Whew, I'm going to need a break after this. I'm already feeling it. If I'm feeling it, I know y'all are feeling it. Okay. Solutions. Solutions are homogeneous mixtures. We talked about solutions and colloids and heterogeneous mixtures. How are they all different? It all has to do with the size of the particles. Okay, solutions, you can filter them. You cannot filter them. And the particle size are really small, okay? They're like 2 nanometers or less. Colloids are bigger than 2 nanometers. The particles are bigger than 2 nanometers. Okay, parts of a solution. You have the solute and the solvent. The solute is present in smaller amount. It's being dissolved. In the solvent. So you have more of your solvent and it is dissolving. The solute. So we talked about solubility, units for solubility, by the way, were grams per 100 ml, grams per 100 ml. But how do we know if something's going to be soluble or not? So that's where we talked about like dissolves like, which all has to do with the type of intermolecular forces between your solute particles and your solvent particles. So polar solutes dissolve in polar solvents. I should say polar or ionic. Non-polar in polar solvents. So we even made a list of some common polar and non-polar solute or solvents. Okay, we said things like water and acetone, methanol, acetic acid. These are all polar solvents. We said carbon tetrachloride, benzene, ethylene. These are all nonpolar solvents. But you have that list written down already. Polar and nonpolar do not mix. They do not make a solution. So after we identified like dissolves like, so remember I gave you a question on exam 4. I don't remember what the question number was, but I said, which of the given solvents would dissolve in certain solutes would dissolve in certain solvents. Yeah, head up. If you got to go, this is not mandatory. The rest of it will be recorded. You're welcome, Rachel. So after we talked about that, we talked about effects of temperature on solubility. Okay, particularly looking at a gas dissolved in a liquid or a solid dissolved in a liquid. We said solids become more soluble in a liquid as temperature increases. And gases become less soluble in a liquid as temperature increases. You have to decrease temperature to get more of the gas to dissolve. I put a question on the exam. I said, if you had a carbonated drink and you put it in your refrigerator, what would happen to the solubility of gas? It should increase because the temperature is decreasing. All right, Henry's law. We said solubility of gas increases as pressure increases. Henry's law, C1 over P1 equals C2 over P2, where C is the concentration with units of grams per 100 ml, and pressure is P, and just make sure units match. If it's ATM and ATM, great. If it's millimeters of mercury, make sure it's that for P1 and P2. And you're given 3 of the 4 parts and you solve for the 4th. Okay, last 3 slides. We talked about concentration for solutions. How do you convey concentration? Like how much of your solute is dissolved in your solvent? So that was weight volume percent equation, which is this. It says grams of solute per, my pencil is probably like on its last leg, per milliliters of solution times 100. So the example problem here is, let's say the concentration of glucose in blood is approximately 90 milligrams per 100 ml. What is the percent concentration of glucose and what's the molarity? So you're given 90 milligrams and we just need to convert that to grams, and then we just plug in 100 milliliters. So 90 milligrams of glucose. We know there's 1,000 milligrams in 1 gram. So we just divide 90 by 1,000. Why did I write times? Equals 0.09 grams. So to get the percent is going to be equal to 0.09 grams divided by 100 milliliters. And remember, you multiply by 100. So guess what happens to the hundreds? They cancel. So our percent is 0.09%. How do we solve for molarity from this? Actually, very easy. We take 0.09 grams and we convert this to moles. I'll write my answer here. We take 100. Y'all, I'm all over the place. Somebody should have corrected me. That should have been milliliters up here. Milliliters on bottom there. We take that. Wait, sorry. I'm looking at the wrong one. I thought that I had it right. There we go. I was converting milligrams. I forgot I was converting milligrams to grams. Then we take our 100 milliliters and we convert this to liters, and we're going to divide these numbers. That's molarity, right? Molarity equals moles over liters. So if we get the moles and we get the liters, we divide the 2. So let's do this. There's 180.156 grams of glucose for every 1 mole of glucose. And then there's 1,000 milliliters for every 1 liter. So I get 0.1 liters and I get 0.0005 moles. So my molarity, when I do 0.0005 moles divided by 0.1 liters, it should be 0.005 molar. Okay, I promise we're almost done. Very proud of all of you. Thank you for showing up. Questions on this problem? All right, molarity as a conversion factor, and then we're going to hit dilutions, electrolytes, and osmosis, and then we're done. Using molarity as a conversion factor. Problem 9.6 is a great example of this. So it says sodium thiosulfate into Na2S2O3, Na2S2O3, the major component in photographic fixer solution, reacts with silver bromide and dissolves it according to the following reaction. So you got this silver bromide AgBr reacts with Na2S2O3, and then it, for some reason, gives you your products down below. Na3, AgS2O3, and sodium bromide. So the question for part A, we're going to do part A and part B. How many moles of sodium thiosulfate would be required to completely react with 0.45 grams of sodium bromide? All right, so we are going to start with 0.45 grams of AgBr, and we're going to convert to moles of sodium thiosulfate. So the first thing I'm going to do is convert grams of AgBr to moles of AgBr, and I need the molar mass to do that. And then I'm going to use a mole-to-mole ratio to convert moles of AgBr to moles of sodium thiosulfate. And looking at my mole ratio here, for every 1 mole of AgBr, it's 2 moles of sodium thiosulfate. So for every 1 mole of AgBr that's going to go on bottom will be 2 moles of Na2S2O3. Okay, there's my mole-to-mole ratio. So I just need the molar mass of AgBr. Silver is 107.87. So we need molar mass of AgBr, and that is 107.87. That is the silver part. Br is 79.9. That's Br. So we just add this up. And it'd be 187.77 grams per mole. And that number is what I plug in right down here, 187.77. Then to solve for part A, which is asking for how many moles of sodium thiosulfate, we do the 0.45 divided by 187.77 times 2. 0.45 divided by 187.77 times 2. And when I did that, I got 0.00, if you round, it's 5 moles. Now, part B is where we're going to use molarity. So part B says if you have a solution of sodium thiosulfate and it's 0.02 molar, how many milliliters would you need to have that many moles in it? How many milliliters of a solution of this concentration would contain 0.005 moles? So I'm going to start with my 0.005 moles. This is using molarity to convert from moles to milliliters, because we know, I'm going to rewrite right here in my problem. I'll just say, I know that 0.02 is that many moles per liter. That's what molarity means. So I want moles to cancel and I want to convert to a volume. So for 0.02 moles, that's 1 liter. And then it says how many milliliters. So I'm just going to do one more step and go ahead and convert liters to milliliters. And I would need 250 milliliters. You should make sure everything cancels right. Moles of sodium thiosulfate, liters cancel, and then you're left with milliliters. Okay. Questions on that? Last slide. Here we go. Solutions. Last part we talked about were dilutions, electrolytes, and osmosis. So dilutions are pretty simple. I'm not even going to work a practice problem. I'm just reminding you of this equation, M1V1 equals M2V2. I'm going to try to put a bunch of equations on your resources page so you have them all in one spot. That'll be up before the final exam. So if I were you, I'd print off the resources page. You might just have the equations. I might go in and label what equations are what. Like this is my dilution equation. This is weight volume percent, whatever. So you're given 3 of the 4 pieces. The biggest thing there is just make sure units of volume are the same. Okay. So if it's in milliliters, make sure they're both milliliters or both in liters before you work the problem. Electrolytes. We said you have strong, weak, and then you have things that we call non-electrolytes. Electrolytes are when you have an ionic compound dissolved in the solution and it can conduct electricity, sometimes strongly, sometimes weakly, depending on what is dissolved. So strong electrolytes, that's going to be something like HCl, which would dissolve into H plus and Cl minus. Fully, you get one single arrow there. That's the big deal. That's the main thing. So what that means is you get all ions. You have no reactant left. Something that's a weak electrolyte, the example I like to use is acetic acid. There's different ways. C2H3O2, that's acetic acid. Wait, CH3CO, and then there should be another H on there. You get a double arrow though. Okay, so you'll get it, it'll break up into H plus and then CH3COO minus. And so you have an equilibrium, all right? When you have a double arrow, that's a weak electrolyte. You might get some product, you're still gonna have some reactant. Non-electrolytes are gonna be something like, what if you have insulin? It's a biological molecule. You might have it as a solid or a liquid, but when you dissolve it in solution, it's just gonna break up into aqueous molecules. Okay, sorry. And so you get no ions. For a week, you get some ions. All right, that's electrolytes. Osmosis and osmolarity. Last things here. Osmolarity is, it's what? It's the number of moles of particles per liter of solution. So you're always asking yourself, you're trying to calculate the osmolarity. We had a really big problem on exam 4 where I showed you a shriveled red blood cell in a beaker. I said, here's the substances in the blood cell, here's the substances in the beaker, calculate the osmolarity of each solution, and then tell me which one's hypo or hyper or isotonic compared to the other. Remember, isotonic is you have 2 solutions with the same osmolarity. Something is hypotonic, it has a lower osmolarity. If something is hypertonic, it has a higher. Higher osmolarity. And the whole deal with osmosis. Okay, so what is osmosis? We haven't even defined it. It is the movement of solvent particles. Actually, just write solvent, don't write particles. It's the movement of solvent from an area of low concentration, I should write solute concentration, to an area of high solute concentration. It's always working to dilute something that is highly concentrated. So that leads us directly to the very last question of the review today. Why do red blood cells swell up and bust when they're placed in pure water? Let me draw us a quick little picture. Got a beaker of water here. And we have a red blood cell. And that red blood cell might have a whole lot of, it might have sugar, salt, all different kinds of ions in it, okay? And the pure water has no solute particles, okay? It's just pure water, it's just H2O. So what's gonna happen is all the H2O here is gonna rush in to try to dilute the red blood cell, because this is an area of low solute concentration. And this is an area of high solute concentration. And so that's why the water will move into the red blood cell